Sure. And in the meantime, I will try to see why Zoom is not allowing me to show my video. I would love to show everybody my face, but
oh, there is a video issue. I'm wondering.
No. I can share my screen. I'm talking about my camera.
Huh. Okay. So I will. In the meanwhile, I'm gonna slowly read your bio. So maybe that right irons out. So Dr. Ravi Mathur is the Director of Research and Development at Emergent Space Technologies. He has been with Emergent since 2012 after receiving his Ph.D. in Aerospace Engineering from the University of Texas at Austin with a focus on spacecraft trajectory design and optimization. He received an MS in Aerospace Engineering from UT Austin for his work on real-time 3D interactive visualizations applied to aerospace software. Ravi has worked on leading mission design projects, including NASA's General Mission Analysis Tool, GMAT, and NASA's Copernicus Trajectory Optimization Tool, and was on the winning team for the 2021 NASA Software of the Year Award for Copernicus. So I would like to say that Ravi also, along with Eric and David, is not new to our university, because last year he was very generous with his time, and we worked on OpenFrames with him and some of our final project students. So this is more of a return, and I would like to say that probably that core of three NASA and NASA associated scientists, Eric, David, and Ravi, were the let's say the critical mass for me to proceed into organizing this workshop, and I'm very grateful for that. So, Ravi, so you're not going to have a camera, from what I understand. Right?
It looks like, unfortunately, I won't have a camera. Okay. But can you see my screen?
Everything is perfect over here. Okay. So we are recording, and we're going to just let you go. Thank you so much, okay. Ravi Mathur, Dr. Ravi Mathur.
Yeah, thank you. So yeah, thank you so much, Fabrizio, for inviting me to this. It was a lot of fun working with you and your students over the past year, introducing everybody to GMAT and to the OpenFramesInterface. So today, I kind of want to just talk about the OpenFramesInterface from the context of using it for mission design visualization in GMAT. I'll start with just a little bit of background on the OpenFramesInterface, as well as its primary dependency, OpenFrames itself. And then I'll start diving into a hello world type of use case and going forward from there, building up on that. So OpenFrames itself is a 3D visualization API that I first created about, and I'm going to date myself here, about 20 years ago when I started graduate school. When I started, my advisor, Dr. Cesar Ocampo, was in the process of creating Copernicus, and he told me that, hey, you know, I don't really know anything about computer graphics. Can you help? We want to have nice visualizations in Copernicus. And 20 years ago was the early 2000s, when visualizations were 3D visualizations were very new in aerospace software. Leading up to that, there was, of course, a lot of 2D plots and looking at streams of numbers and things. And so what I did, I have a background in not only astrodynamics, but also visualization, computer science, computer engineering, software design. So I looked at the aerospace field, and I did notice that there was no at the time API that people could use to add 3D visualizations to their own aerospace or science or engineering software. And so I set out to create what became OpenFrames, which is an API that you can use to add 3D interactive visualizations to your own science and engineering software. It's been around for about 20 years now. There's no computer graphics knowledge required to use it. And there's no significant software architecture changes needed on your own application in order to use it. That was one of the critical things. Copernicus already existed, GMAT already existed. We don't want to have to ask those applications to redesign their architecture just to fit in visualization. Instead, the visualization should fit into their existing architecture. And it has a lot of other features like multi-threading, so that visualizations happen on separate processing cores and don't significantly slow down the simulation itself. I released it open source because I kind of foresaw even 20 years ago that this was something that could only gain traction if it was easy to incorporate into other tools. So as it stands today, OpenFrames is used in several mission design and also non-mission design, but generally science and engineering software tools. GMAT, of course, is the one we'll focus on today, but there's also Copernicus. There's Virtual Landscapes, which is a VR-based tool out of NASA Goddard that's also open source, and that they use to analyze huge numbers of stars in the galaxy, on the order of tens to hundreds to billions of stars in VR, and see how the stars move forward and backward in time. So of course, we're going to concentrate on GMAT. The point of this graphic here is to show that OpenFrames works regardless of, almost regardless, I should say, of what language your own tool is written in. So for example, GMAT is written in C++. Copernicus is written in a combination of Python and Fortran, and Virtual Landscapes is written in C++. And it also works regardless of which type of GUI toolkit your software is using. So GMAT under the hood is using something called WX widgets. Copernicus now that it has its new Python GUI, is using Qt, and Virtual Landscapes is using Qt also, but in a VR only sense. And so OpenFrames will allow each of these and even more use cases to integrate with OpenFrames and provide visualizations for those tools. And under the hood, like behind the scenes, OpenFrames is integrating with 3D graphics technology and VR technology to do the actual rendering. But all of that is kind of opaque. How it does the rendering either to a monitor or to the VR headset is opaque to the tools that are using OpenFrames by design.
And can I ask a question?
Yeah.
We have been counting computer languages today. Finally, the one I love has made its appearance. So I see Fortran there listed. So as you probably will know, Copernicus cannot be distributed to us because of some,
Yes, it's government.
So right. So that's fine. But I am curious, is it possible to know why Fortran was chosen for Copernicus without disclosing any other information that you may know?
Fortran was the language that Cesar Ocampo knew. He was my advisor at UT, the person who made Copernicus.
Oh, that's it. Okay, I see.
Very simple reason.
Okay, so but that makes me feel good that when I tell the students that Fortran rocks, I am not necessarily, I don't belong to the 19th century. That's what I'm trying to say.
The person who is now the lead developer for Copernicus is a civil servant at NASA Johnson Space Center, and he goes to Fortran conferences to talk about Copernicus.
Okay. Right.
So it is not. It's not like Latin.
Yeah. You got it. Thank you. Sorry.
At least within the aerospace community.
Sorry for the interruption. I really like.
Oh, that's fine. I actually enjoy the interactive nature of these workshops. So I'm more than happy for anybody to chime in at any time. Questions.
So I'm happy that the students listen to this. So thank you so much.
Okay, so that's just a quick background on OpenFrames itself. Now let's get to the OpenFramesInterface plugin for GMAT. So leading up to GMAT, prior to GMAT R2020A, GMAT has had for its entire history this graphics component called the orbit view, which was what provided 3D graphics to GMAT for the longest time. The issue with it is that it was very hard to maintain or upgrade just by virtue of the way it was designed. And it has other limitations, like it slows down the actual computations of GMAT significantly. And so what we found was, even in using GMAT, a lot of people will just disable the graphics so that things will compute faster. There's other limitations to orbit view also, but after working with GMAT for some time, what I realized was, I can use OpenFrames in GMAT also to give it a lot more features, to make it more high performance graphics, and make it so that the graphics can actually be updated with new features and new capabilities over time. And so we at Emergent, we created the OpenFramesInterface, which is an open source plugin for GMAT. We did this through the NASA SBIR program. And we started, I think, in 2016, so over several years, and a lot of testing, a lot of end user testing, development, all that. We were able to release it with GMAT. So now the GMAT project includes the OpenFramesInterface as part of its release, starting with GMAT R2020A, which I believe all of you have been using. Well, some of you have been using. It also, I wanted to point out, does work with Daryl's Astrodynamics Workbench tool that he mentioned during his presentation. So, and in fact, I think all of the graphics that you saw in his presentation were using that.
So at this point, sorry, I'm confused. So the Astrodynamics Workbench is another independent FOSS tool?
Well, Daryl, you can say a couple words about that if you want. Because he had brought it up at the end of his presentation.
Right,
so.
but because he deferred to you, I thought that it was something that was associated to OpenFrames, but I misunderstood clearly. So
no, Astrodynamics Workbench is something associated with thinking systems. Daryl,
I don't know. Okay, I see. Okay, yeah. Okay. I'll ask him. Thank you so much. I get it.
Yeah.
And thinking systems is still not sure what their business model is for it yet. So
yeah. So go
ahead.
Yeah. Okay. So my point here is that it's included with GMAT R2020A, and many of your students have been using it already. It's compatible with all existing GMAT scripts. And the point of saying that is that you can take scripts that you've been writing that you may have been using Orbit View and simply add the OpenFramesInterface. I'll show you how, without having to modify other parts of the script or rewrite it, things like that. It comes with several GMAT sample scripts, I think about 20 now, and it's been tested on Mac, Windows, and Linux, so it works on all three platforms. I myself develop primarily both on Mac and Windows, and Daryl helps with a lot of testing on the Linux. Okay, so hello world. Let's. I'm going to go through a few examples of how to use the OpenFrames interface. We'll start simple, and a lot of your students will probably recognize a lot of this. And then we'll progressively get a little more complex. So the first one, the goal is to create your first OpenFrames interface window. We'll look at how you can do things like changing views, controlling time and animation, synchronizing time between multiple OpenFrames interface windows. Viewing the scene in VR, if you have a VR headset, switching to printer-friendly mode, which I've gotten a lot of questions about. Can we do this? If as you know, if you want to put graphics into a conference or a journal paper, a lot of times you want to switch it so they have a white background for printer-friendly mode, and so this supports that also. And how to get to the OpenFrames interface help page. So this is just really the very initial hello world kind of example. So let me open up, I'll do all this through GMAT. This is GMAT R2020A, basically what you could download. When you run, if you just open up GMAT and run it, what you'll get, and you may be familiar with, is an orbit view window here at the top and a ground track. So adding the OpenFrames interface itself is as simple as right-clicking on output and saying OpenFrames interface, right? Because it's included with GMAT, there's nothing extra to install. It just comes with it. Then if you rerun the mission, you see it here. And so, like I mentioned, it comes with the ability, and all these things that I'm going to talk about are things that you cannot do in the old orbit views. So there's specific features for the OpenFrames interface. So you can switch views to look at pretty much any object in your scene. And we'll talk later about how you might be able to create new views to look at additional things. You can control time and animation easily, which you would think would be a very common feature, but what was not there previously. Now you can pretty much go to any time in your mission. You can even specifically go, to an exact time if you want to. You can animate forward and backwards at varying time scales. So this has been a very useful feature for a lot of people, the ability to animate in terms of showing your mission to other people, showing the animation. In the orbit view, you could animate, but it didn't animate correctly in time, meaning if you had an orbit with a low periaps and a high apoaps, the spacecraft would go slower at periaps than it would at apoaps, which is the opposite of what happens in real life, right? So you can also, if you have multiple OpenFrames interface windows, let me create another one. Let's add another OpenFrames interface window. You can synchronize time between them. So if you just double click on it, just like you can with any other component in GMAT, you'll get the settings window. And I can say I want to synchronize time for this OpenFrames 2 window with the OpenFrames 1 window. And if I apply, now if I change time on either of these, the time automatically changes on the other one too. So this is also a very powerful tool in the sense that if GMAT is running, for example, in a mission operations center or something, and in which case they frequently will have multiple windows open, it's easy to make sure that you're looking at the same time between all of them. All right. VR headsets, I will just show quickly how you can do it. Some of you may already know it. Obviously, there's no sense in me actually enabling it here because I don't have my VR headset connected. If you double click on OpenFrames, it'll open up the configuration panel, and in graphics options, it's as easy as just enabling it. And if you have Steam VR installed, which works on Windows and Linux, I think I don't remember, Daryl, if you've tested this on Linux. I know we've tested it a lot on Windows. You are able to view the entire scene in VR, and the nice thing about that is you actually get a lot more context of what's going on with your trajectories, especially if you have complex 3D trajectories, right? Not just planar motion like this, but if you have really complex 3D trajectories, you get a lot more information looking at it in VR than you do on a flat computer screen. Okay, and then the last thing is switching to printer-friendly mode. So for that, I'm going to open up. Let's see where I have this.
And Ravi, one question
Yes.
is, can you give? I mean, I don't know if it is allowed to give a specific model and brand that this was tested with, as far as the VR set. What would you suggest?
Sorry, can you ask that again?
When you say to use the virtual reality set.
Oh, yeah. So I have tested it with the Oculus Rift, the HTC Vive, and the Oculus Quest.
They are all the equivalent, do you think?
Which are the three biggest ones, like the high end. Yeah,
okay.
Yeah, and they'll all show the same thing. You can use the controllers to change the view and all that stuff in VR. The nice thing about the Oculus Quest is that it's wireless, and so there's ways to wirelessly connect it to your computer and still basically get wireless VR in that sense.
Yeah, well, great.
Nice.
Thank you.
Yeah. So in order to get printer-friendly mode, let's open up the GMAT script. And for the sake of, I'm actually going to just close these windows just for the sake of making things a little easier. Let's get rid of this one, just so we can simplify what's on screen. Printer-friendly mode is it's accessible through the script, not in the GUI right now. So if I go into the script, I have the section of the GMAT script, and I'm assuming that people have used GMAT and have some very basic knowledge of how to interact with its script, which I think is probably a safe assumption.
No, we haven't. However, there is a lot of Octave and MATLAB experience.
Okay. So. And then also after Daryl's presentation, right, which he focused a lot on.
Yeah, I think that Daryl was the one that really brought it home. Yes, thank you.
Yeah. So it's when you go into the GMAT script, as Daryl mentioned, there's different sections for the different components, and so you'll see a section in the script that talks about the OpenFrames interface component, right, and lists all the different options that it has. And most of these are reflected in the GUI, but specifically the printer-friendly option is not reflected in the GUI. It is called, and I'll show you where you can look these things up later. We can say star settings equals printer. And so I save it, and then I run it. It switches to just a white background, right? So I wanted to point this out because I get a surprising number of questions of people asking, how do you do this? And so,
and I have one related question to the. This is wonderful, really. This is very useful. The question is, can you export it to a vector format?
No, I also get questions about taking screenshots. That's essentially what you're asking, right?
Yeah.
Yeah, and my recommendation so far, I may add a screenshot capability, but my recommendation has always been every operating system has screenshotting built in. And so like in Windows, you can take screenshots. On Mac, you can take screenshots, and on Linux, you can take screenshots. So I usually just recommend to people to just use the OS native screenshot capability.
But my question is a little different. So yeah, I mean we do that, and that's exactly what we end up doing. But it is a lot higher quality for journal publications to output a diagram to EPS or PDF. And
yeah, that's a good point. And so it's on my roadmap for the OpenFrames interface to add native screenshot capabilities where you can save it out as a TIFF or a PDF or something like that.
Okay, lovely. Thank you so much.
Yeah. Okay. And then the last thing, just for this simple one, is you can always go into if you want to see all the options, you can always go into the configuration panel of the OpenFrames and just click on help on the bottom right. It'll take you directly to the wiki that explains the different options for all the different panels. And so that's a useful way to look at things. All right, so let's get back to, let's close this. All right, so we took a look at the very initial high level parts of the OpenFrames interface that many of your students may have been familiar with some of these already, right? So next step, let there be light. So we want to enhance situational awareness here, and we're going to do that by adding the sun for simple lighting. And in a future version of the OFI, we're looking at adding shadowing also, right, for even more situational awareness. And adding vectors that point to other objects and changing the spacecraft model itself. So as of OpenFrames Interface R2020A, those are the available model formats, and we're looking at adding more 3D model formats, support for more formats in future versions. And so let me start GMAT up again.
So it's not just, I was under the impression that 3ds was the only one. There are others also?
So 3DS is the only format that GMAT itself supports through the orbit view. But the OpenFrames interface supports more formats.
Oh,
And so I'm going to show you how,
okay.
how you can.
Wow. All right.
Yeah, I'm going to show you how you can do that.
It's Christmas. Okay. Thank you.
Yeah.
All right.
Yeah, it's useful. So let's start this again. I like to start each one of these examples kind of from scratch. And in this one, we're going to get rid of the orbit view and the ground track plot because we don't care about them. And let me just save this. Desktop, let there be light. Okay. So when you just start a default OpenFrames and you look at what all is selected, it will by default visualize your spacecraft, the main spacecraft that's in the script, as well as the Earth. If you want light, you add the sun. It's that simple, right? Right now, the sun is at the center of the Earth because we haven't propagated it. It doesn't know where to put the sun. So we just rerun the mission and the sun goes in the correct place. And now we have better awareness. It's not a full lighting model, it's a simplified lighting model. And you can see, right, the dark side and the light side of the Earth that changes as you change time. So if we, clearly the sun should be over here on the left, which is where it is. Let's go over to the spacecraft. Sometimes it's useful when you're looking at the spacecraft to know where the sun is. You can get context clues for that from which side of the spacecraft appears to be lit up. But you can also, you can also add vectors to, for example, point to the sun. So if I open up the configuration panel again for the OpenFrames interface, I can add a new vector. I'll tell it that it should be at the source of the spacecraft, and the type should be a relative position, and I want it to point towards the sun. And let me just call this sun vector, and the label should be sun, and we want to make it yellow. All right. Now you see this, and you can add as many of these vectors attached to whatever objects pointing in either body fixed directions or pointing towards other objects. And this helps you maintain that situational awareness of, you know, in space, things are far away and not everything is on your screen at the same time. So it can be nicer to tell in which direction something is. And these vectors dynamically always point in the correct direction, right? So this is pointing at the sun. All right. Let's see. So that's vectors. That's adding simple lighting to the sun. And now let's take a look at changing the model. So as I said before, in GMAT itself, you can change the model of a spacecraft if you go to the in the GUI, which many of you may be familiar with. If you go to the options for the spacecraft, you go into visualization, you can set a model here. But if you want to set a model that is not 3DS, then you go directly into the script and you go into where the spacecraft is defined, which is usually at the top of the script, where we say create a spacecraft, and then it has all the different options for the spacecraft, right? And in here will be an option for model file. And you can actually change this to any other file that you want. I had set this up on my other computer. I don't remember if I have the appropriate model on this computer. Let me see if I do. Desktop. Well, I have a 3DS model with OSIRIS-REx. I'll just use this for right now. But you can do other models. Heck, I wonder if I could just do Bennu. This should make things interesting. I'm going to put Bennu, the asteroid, as the spacecraft, and we'll see what happens. Okay, we're just going to take the file name and drop it into here. Make sure it's a relative path. So it's an OBJ. And now if I go to the spacecraft, I see the spacecraft is an asteroid, right? So I just did that for, you know, impromptu because I didn't have the same form, the model was on my other computer that I wanted to use. But the point is, you can use any one of these supported model formats in there.
You put Bedu orbiting around the Earth, basically.
Yeah, just for fun, because
okay.
You know, we may
sounds
want to
good.
bring an asteroid back to the Earth one day anyway.
Good
So.
point. Good point. Fantastic.
Okay, so that is this little tutorial. Let's go to the next one. In the next one, we want to look at, do you see what I see? So we want to visualize what a sensor sees. So let me close GMAT and start it back up again. We want to visualize what a sensor sees. And so in the OpenFrames interface, you can add sensor masks. And I'll show this in a minute. You can add sensor masks to either ground stations or to spacecrafts. And then you can change the viewpoint of your camera so you are seeing what that sensor might see. And so a sensor may be a camera that's on a spacecraft, you know, if it's a spacecraft that's looking towards the heavens or looking back down at Earth for Earth science. Or a sensor can be something that's a telescope pointing up from the ground in a direction, right? Or any other type of sensor, basically. And sensors have fields of view, and so you can define different fields of view in GMAT, and then you can visualize them with the OpenFrames interface. So let me go back to GMAT, and there's already a sample of this, so I'll open up that sample. And this sample comes with GMAT. It is called the field of view sample. All right, so what you're seeing here is a lot of things. One, you're seeing the Earth with a ground station at Tucson, and this ground station has some very complex, let me switch over to the view of it, has a very complex antenna mask, right? As you can see, where it's defined by a series of clock and cone angles around the ground station, right, of what it can see. There's also multiple spacecraft that are orbiting the Earth, which are looking at the Earth, and all of which have different types of sensors attached to them. So let's go to spacecraft 1, which has a conical sensor attached to it. Spacecraft 2, which has a rectangular sensor attached to it. And spacecraft 3, which has a custom sensor attached to it. And you'll see what this sensor looks like. Well, you can see it kind of here. Looks like an arrow. If I go to any of these spacecraft and if I reset the view using the reset view button, I'm looking straight down the bore side of the sensor and I see what the sensor sees. This is very useful in practice for being able to understand, first of all, just what your sensor sees, but also there's times when you're designing spacecraft and you want to know, where should I put the sun sensor on my spacecraft? If you put the appropriate sensor mask using GMAT and look down the bore side of the sun sensor, you can see if other parts of the spacecraft are impinging on what that sensor would see, right? So you can see if other parts of the spacecraft are blocking, like for example, your solar panels may be blocking the view of the sun sensor or things like that. It just helps you to place components on spacecraft during the design phase. And it also helps you to be able to estimate what the spacecraft would see, even operationally or during design, right? So in this case, I'm not going to start this one from scratch because it takes a while to do it, but this example, this sample script comes with GMAT. This is the field of view sample script. But in this one, we have multiple spacecraft that we've defined. And in the OpenFrames interface, you can create different sensors, right? So in this case, I've created multiple sensors already. Let's take a look at one of these for the spacecraft 1. You say the source object, so you pick which spacecraft the sensor is attached to, and then it will give you a list of sensors that are already attached to that spacecraft. These are sensors that are defined within GMAT itself. So I'm not going to go into the GMAT part of how to add them here, because that's a separate thing that I can, of course, Fabrizio, we can talk about that offline, and I can help you to understand how to do that if you'd like. But once the GMAT sensor has been defined, yeah. So once the GMAT sensor has been defined, then in the OpenFrames interface, you can visualize it, right? So you can select a spacecraft, or in this case, there's also sensors on 2 different ground stations, Canberra and Tucson. And then it'll tell you what are all the sensors that are available for that object that you selected. And you can name it and so on and so forth. All right. Let's see. I think that is, do you have any questions about anything that I've been showing so far?
I remember when you were discussing these issues with, remember there was that student Yaren Boyage,
Yes.
And yeah. So you were actually teaching her how to put an ultra detailed map of the Earth at the.
Yeah, that's going to be the next thing.
Okay, great. So that's my
you
okay,
read
great.
my
Okay.
mind.
Okay.
All right, next one, watch out for the ground. So this is a relatively new thing in the new feature in the OpenFrames interface, which is the ability to use high fidelity terrain models. In order to do this, you need the terrain add-on to the OpenFrames interface, which you can ask Fabrizio for this because I've given it to him, or you can just directly ask me for this. My contact info is at the end of this presentation. It works only on Windows right now. We've tested it on Windows 10. There's roadblocks to implementing high fidelity terrain on macOS, and Linux support is coming in the future. Again, Daryl, I can't remember if this was something that you had tested on the Linux side of GMAT and the OFI or not, but I know that we've tested it a lot on Windows. So let's go into GMAT. GMAT. I'm going to open up a sample script that comes with GMAT and show it first before we get into the how did we do this. High fidelity Earth Moon. Okay, so what this is doing is, previously I showed you how to replace a spacecraft model with your own custom model. In this one, what we're doing is we're replacing the Earth and the Moon with a custom model. And that custom model is something that loads terrain dynamically. So let me go over to, so now we're changing the view to look at where the Keck Observatory is in Hawaii, right? Let's change time so it's not quite as bright. And what's happening is, as I go to different places on the Earth, on the back end, this is loading in real time from the internet data about the terrain and about the imagery on wherever on the Earth I'm looking, right? And so this requires an internet connection because it's loading in tiles in real time from a remote data source. For the Earth, everything is available on the internet, so there's not really any extra work to be done. I'll show what is the scripting and the input files part of this in a bit. When you go to the Moon, it's a little bit of a different situation, because for the Moon, imagery for the Moon, this might take a little bit to load. Imagery for the Moon is available online, which is loading. Let me actually move to a different part. Let's go to Compton. Yeah, there we go. Imagery for the Moon is available online, and terrain is available online also, but terrain is not available in a format that's easy to load. It's like one huge 10 gigabyte file. So what you have to do is download that large file and tile it on your computer using tools that I distribute with the terrain add-on for the OpenFrames interface. So I won't get into like what is the command line, command that you issue to convert a huge 10 gigabyte terrain file into tiles. We can that comes with the instructions on how to use the terrain add-on. But for now, I'll leave it to you to know that for the moon, you have to do some work offline on your own computer to download a large file that covers the terrain of the entire moon and then tile it. And that's a one-time task that you do ever on your computer. And then after that, the OpenFrames interface can load that tile data locally for the terrain from your computer, and then it'll go to the internet for the imagery of the moon. All right, and so you can see this is actually a recreation of I think the image that LRO took quite a while back about Earthrise. It's the image of Earthrise. Oops, view. Let's go back to Compton view. And this is over the Compton crater at the moon at a certain time where the Earth happens to just be rising over the moon, over the horizon of the moon. And when we look at this image and compare it to the real image, of course, if I take away the artificial vectors and names and everything, everything does line up in terms of the orientation of the Earth and the moon and the lighting and all that stuff. So that's one way in which I validate the results of the OpenFrames interface is really just by comparing it to real pictures that spacecraft take as they're traveling. I did a lot of comparisons to OSIRIS-REx and pictures that it took of Bennu and pictures that it took of the stars and pictures like this that LRO took. Compare them basically side by side. What do you see in the OFI and what do you see in the real image, and see how well it matches up.
And I have a question regarding,
yes.
because again, going back to one of the groups of students that was speaking when it was still night where you are, but one of them is doing autonomous navigation. So the question is, if you can you simulate with OpenFrames something like asteroid navigation of a spacecraft in the solar system by because I mean GMAT does have a star background, right? There is a sky background of stars.
Yes. Yes.
So is it possible to have asteroids in the field and use OpenFrames to simulate?
Yes,
imaging?
I have. Yeah, I've actually replicated the OSIRIS-REx mission with GMAT, with the OpenFrames interface, and actually I did it side by side with the OSIRIS-REx team while they were in the Mission Operations Center, so that we could see what their tool would have produced as the estimated image versus what OpenFrames interface was producing, as a way of kind of shadow validating the OpenFrames interface. And so yes, you can do that. You can like I showed in the previous one, where you can see out of a sensor, right? You can simulate in some way what a camera on the spacecraft would see, and then as you approach the asteroid, you see the asteroid in the field of view, in the correct size, the correct orientation, and as high fidelity as the asteroid model that you have, of course, right? And so yes, you can do all that with the OpenFrames interface I'm just trying to think how much I can say. We've also looked at situations where we use OpenFrames and the OpenFrames interface to generate images that are then analyzed by other algorithms to find features or things like that.
Great. No, that's amazing. Yeah. Okay, so group one, I think that we may have a solution for that. Fantastic. Okay, thank you.
Yeah. You're welcome. Okay, so that's the high fidelity terrain. For some reason, Copernicus crater is taking a long time to load. The internet source for this can sometimes be a little bit slow. So I'll go ahead and close this for now. All right.
Yeah, and it was coming.
Yeah, it was coming slowly.
Slowly. Thank you.
What's happened is 1 year ago or so, the internet source for that was extremely fast. And then I think a lot of people started using it, so they started throttling requests. And so what I see now is I'm only allowed to receive like 1 tile per second or something like, or 2 tiles per second. Whereas before it would just stream in extremely quickly. And so I may look for other sources, or of course, what you can always do, like I said, must be done with the terrain. You have to download the large terrain map, which is like 10 gigabytes, and tile it on your computer. You can also download the image, the large image, and tile that on your computer, so that everything is loaded locally and you're not hitting the internet for anything.
Yeah, great. Okay, thanks.
Yeah. Okay, so future work for the OpenFrames interface going forward. Of course, the terrain stuff, while right now it is an add-on to the OpenFrames interface, it's going to be included as part of the next GMAT OpenFrames interface release. Some of the things that I am looking at for the OFI are trajectory trails and traces. Right now, it shows the entire trajectory of a spacecraft. But of course, I've gotten a lot of requests to be able to show only a subset of that. Like, for example, show me where the spacecraft is and up to where it was 1 hour ago, or 2 days in the future, or whatever, right? Don't show me the entire trajectory. Just show me a part of it. Another huge thing that we're looking at, which doesn't exist in any mission design software at all, is visual interactive trajectory design, which is essentially just being able to visually grab and drag the spacecraft. So if you imagine, if I were just to, in this picture, this is OSIRIS-REx and that's Bennu in the background. Just be able to grab the spacecraft and move it and see how its trajectory changes. It is an extremely powerful teaching tool, and an extremely powerful tool to understand the design space. So both for students and for professional designers who are doing early mission design, to try to understand how does the spacecraft trajectory change as I move the spacecraft around, or change its velocity, or if I have a finite burn, change the start or end time simply by visually grabbing and dragging things with your mouse, right? As opposed to typing in numbers and then typing in different numbers and seeing what happens. So one place where this exists is in games, like Kerbal Space Program. If any of you have played that, you can do that in Kerbal. It also exists very much in movies and science fiction and things like that. If you see how people do trajectory design on shows, they're always just grabbing and moving things, and it looks amazing, but it can't be done right now. But we're looking into how to do that, and we've shown that in a prototype you can do it with GMAT and the OpenFrames interface. And we're looking into full implementations of that.
When do you, when we're saying future work, do you have a time horizon for this?
We don't. Well, the first one is the time horizon of the next GMAT release, which I think Daryl mentioned, are 2022, later this year. These visual interactive trajectory design, I can't really talk about the time horizon. But hopefully not too far in the future, and it's something that we'll demonstrate it as we go.
Sure.
Right, we'll put up YouTube videos and things like that. We've got videos on our. I put the link to our YouTube page. You can see videos of the OpenFrames interface. You can see videos of OpenFrames working in other tools, and so yeah, there's a lot of bug fixes based on things that users have reported over the past 2 years, both bug fixes and performance improvements, new features here and there. So this is an actively developed component.
Sure.
Right? So I think that is it. We're about 5 minutes early or so.
Yeah, you are as accurate as GMAT. Really, very good. All right. So this is fantastic. I mean, you got my head spinning about the pedagogical potential, and that is really amazing. This, the idea of grabbing the spacecraft and moving it around, it looks like Star Trek, probably the next generation or something. It's not.
Yeah.
So,
We have a video of it on our YouTube channel of Visual Interactive Trajectory Design, which I think is this one right here. But I won't stream it. It probably will stream slowly if I share my screen. Y'all can just see it yourselves. But
so Emergent. So
with Monday.com Work OS.
I'll show just the very simple parts of it. It's essentially just moving a spacecraft, right? Rotating around, which is analogous to changing its velocity vector in this case. And I show how you can find a lunar free return trajectory very easily, just visually, without having to type in numbers or anything like that.
Well,
that's interesting work.
It's
very hard because you have to think of a lot of user interface paradigms, right? Typing in new initial guess numbers and modifying those numbers is one thing, but figuring out how do I allow a user to click and drag a spacecraft and what does it mean to do that is a very open-ended question. A lot of research involved behind it.
And there goes the homework, because my students had to find the free return trajectory, but with your solution, it's gonna be pretty useless
no
homework. Really. All right. So okay. So Ravi, this was high power, high energy. Really, I'm absolutely delighted. And I wanted to ask you, the presentation itself is not available. The PowerPoint I'm talking about. I
can send you. I'm happy to send you the PowerPoint, then you can distribute if you like.
Only internally to the university. I'm talking just for my students to follow up on what you have done. If I will ask all the speakers, but of course I respect your wishes. So and I want you to know that my students are terrorized about not citing. So if they cite. No danger there. All right. Thank you. It was fantastic. Thank you.
Yeah, you're welcome. Thank you.
Thanks for returning to Izmir. And I would like you to know that, as I've told the other speakers, we really count on seeing you here in town at a future edition of this workshop, hopefully to show you around our beautiful city and continue the conversation with the others locally, face to face.
Yeah, thank you. I'm sorry about my camera. I saw the message from, I think, one of your students that it may be disabled. I'll have to look at it. It works sometimes, it doesn't work sometimes. I don't know if there's something wrong with my camera, but either way,
yesterday night it was amusing to see a bunch of space scientists wondering how Zoom works. So it's great to see you. Great to see you again. Unfortunately, we have no time for questions unless there are pressing questions from the audience. Okay,
I'm happy to take a couple quick ones if people have them.
Any questions? Okay, we'll stop here then. We'll stop the recording, Ravi, and thank you so much again.